Welcome, ladies and gentlemen. It's great to see you guys. Let's go ahead and take a look at our fundamental theorem of calculus, both parts. And so, while the definition of the definite integral includes the limit of a Riemann sum, right, as the number of rectangles, n goes to infinity, or the width of those rectangles, delta x shrinks to 0, and we sum up the area of all those rectangles, we're left with the exact area between my graph of f and the x-axis in between a and b. But that wasn't why I was looking for the definition of the definite integral, right, which is what this is equal to. Rather, how we can evaluate that exactly and algebraically using antiderivatives, right, without rectangles, without trapezoids, and without partitioning my interval into n equals subintervals. So how do we evaluate that, Marissa?
Big F of B minus big F of A.
Absolutely. Big F of B minus big F of A, where F is an antiderivative, any antiderivative of little f. So I'll go ahead and say that is where F prime of x equals F of x. So big F is an antiderivative of little f. Raise your hand if you had number 1. So there's my evaluation part of the fundamental theorem of calculus. Great. The antiderivative part says explicitly that differentiation and integration are inverse processes. Whatever one does, right, to my input integrand function, the other one undoes, and I get back right where I started. But the key difference here is that my independent variable is the upper limit. So a could be any constant, right? A could be any constant. And if I were to find an antiderivative for little f and evaluate my upper limit, in this case my independent variable x, I get big F of x minus big F at a. A is a constant, and differentiating big F of x produces little f of x. I get right back to my integrand function, and then minus the derivative of this constant is 0. So I can now forever ever have to go to the shortcut. This is simply my integrand function evaluated at my independent variable. Raise your hand if you got f of x. F of x, that's it. There's my fundamental theorem of calculus. Let's apply. So I can evaluate a definite integral exactly and algebraically without the use of rectangles and without the use of my grapher. How do we do it? We find an antiderivative function for my integrand function. So we need to remember our derivative rules in order to find antiderivatives. Looks like this is going to be a power rule where I add 1 to the exponent and divide by the new exponent. So the current exponent is x to the negative 2. Adding 1 to the exponent gets me x to the negative 1 dividing by the new exponent makes it a negative. So I get negative 2 over x. Raise your hand if you had that. Negative 2 over x. Awesome. And we'll evaluate from negative 2 to negative 1. So I'll go ahead and put my upper limit in all the way through. And I get negative 2 over negative 1 minus. And I'll put my lower limit all the way through. And I'll try not to mess up all the signs. And so what's going on here? It looks like negative over negative is positive, minus, oh gosh, this is going to be a positive, so minus, and then 2 over 2 is 1. So I'm getting 1. Raise your hand if you got 1 for the first one. Did you get 1? You did? Yes! Hey, we agree. That's good news. Let's take a look at number 4. The integral from pi over 6 to 5 over 6 of cosecant squared of theta with respect to theta. So we need an antiderivative for cosecant squared. What function did you use for the antiderivative of cosecant squared? Any?
Negative cotangent.
Nice. I know that cotangent of theta, I'll make that a little bit bigger. I know that cotangent differentiates to opposite cosecant squared. Therefore, negative cotangent theta must differentiate to positive cosecant squared theta. Evaluate it from pi over 6 to 5 pi over 6. Awesome. What a great chance to work with our exact values and trig functions. So here we go. 5 pi over 6 in the cotangent. Recall cotangent is the quotient of cosine over sine. And so 5 pi over 6, my cosine is negative root 3 over 2. My sine is positive 1/2. That's going to reduce to negative root 3 over 2. But my function has negatives. So I get negative root 3, so positive root 3 for my first. Is that right? So cosine over sine, cosine. I'll do it again, Marissa. I don't mind. I'll do it a third time. So 5 pi over 6 cosine is negative root 3 over 2 over sine is positive 1/2, so that's a negative root 3. But I had a negative on my cotangent, so that's positive root 3. I get root 3 twice. Minus, now let's evaluate. the value of negative cotangent of theta when theta equals pi over 6. So pi over 6, cosine is positive root 3 over 2, and sine is 1/2, so that's positive root 3, but I had a negative, so negative root 3. So I'm getting I'm getting root 3 minus a negative root 3 is root 3 plus root 3 is 2 root 3. I'm getting 2 root 3. Oh gosh. Here's the moment of truth. Raise your hand if you had 2 root 3. Did anyone else get that? You did! Hey! That's better than a poke in the eye. Oh, goodness. Keep in mind that we could always check any of these with our Math 8, find an integral on our calculator numerically, and get the decimal approximation for that, and then compare. All right, what questions do you have about 3 and 4? And then 5 and 6 will be application of our fundamental theorem of calculus. The second part, the antiderivative part. And so I know the derivative of an integral expression is simply the integrand function evaluated at my limits, at the upper limit, as long as the bottom limit is a constant, provided my upper limit is the independent variable, like x, or in this case, m. But it wasn't. It was a composite function, 3m. And so when I differentiate, I need to apply the chain rule. That is, the derivative of the integral expression is the integrand function with the inner function, that's my upper limit, and then times the derivative of my inner function, that's times the derivative of my upper limit. And so that's just going to be a times 3. So I'll rewrite the original 2 minus sine of all over 3 plus cosine of, but I'll substitute in my upper limit 3m everywhere my integrand function accepts inputs. Then times the derivative of my inner function, which was the upper limit, which is 3. So I get 3 that, and so if I wanted to make it look prettier, I could rewrite one time and get 6 minus 3 sine of 3m all over 3 plus cosine of 3m if I wanted to, but don't have to. Raise your hand if you got that. Did anybody get this one? So again, several of you know. What questions do you have about 5 then? You got it? What questions do you guys have about 5? Let's do our final one. The derivative with respect to x of the integral from sine of x to cosine of x of t squared with respect to t. Yikes! So the derivative of an integral expression is simply the integrand function evaluated at my independent variable if my lower limit is a constant and my upper limit is plain Jane x, the independent variable, or m, or theta. Problem is here, I've got an upper limit that is itself a function of x, cosine of x. To compound matters, my lower limit is also, right, a function of x, sine of x. That's okay. I can combine the evaluation part of the fundamental theorem of calculus along with the antiderivative part and go ahead and subtract my upper limit eval, right, minus my lower limit eval. The derivative of that is going to spit out at times the derivative of my limit. So this is just going to be 2 expressions with subtraction. That's the evaluation component, right? And then I'm going to be times the derivative of my limit attached to each of those. So let's go ahead and see what that looks like. Ready? Integrand function evaluated at the upper limit would be cosine squared of x times the derivative of the upper limit would be cosine differentiates to opposite sine of x minus the integrand function evaluated at the lower limit. The integrand function evaluated at the lower limit would be sine squared of x, then times the derivative of the lower limit in accordance with the chain rule. It's going to spit out a cosine of x. So I don't know if there's a pretty way to write this. I was hoping we get a nice identity like a Pythagorean, sine squared plus cosine squared, but I don't think we do. I think we get negative sine of x cosine squared of x minus cosine of x sine squared of x. Julie, can I pull out a... No, it's not going to help. If I pull out a sine of x, then I still have sine cosine, and then I don't have enough anyhow. So it doesn't really matter. I mean, yes, we could factor a GCF out, but it's not going to give us an identity. So I'm going to leave it like this. All right, I'm dying to know. I want to put this one last because I want to see how you guys handle the limits. So, did anybody get this? Anybody go? Yeah! What do we got this one in the 5? Cool. What questions do you have about today's hour? I'm gonna go ahead and pause the recording then while we take care of our OTL check. Go on. Okay, ladies and gentlemen, so recall our definition of the area accumulator function f of x. And so if I let big F equal the integral from a constant, right, up until my independent variable of some integrated function f of t, then I know the derivative, so long as my lower limit is constant, the derivative of big F equals what? What's the derivative of big F given by? Tyler? F of x, absolutely. That's the integrand function evaluated at my independent variable. So f of x. That's great news. So now I can use this relationship, right, to answer all kinds of questions depending upon which function I'm given, right, and which level of the elevator I'm on. I can answer questions about increasing, decreasing behavior, extrema, concavity, etc. And so let's suppose that we had a picture of f, whose graph is shown, and then a new function, p, given by the integral from constant to x of f of t dt. All right, so if p is given by the integral from constant to x of f of t dt, that means that p prime is what? Go ahead and share with the class when I call on you. So if p is given by the integral expression, then what is p prime? Vivian? Pardon? It's f of x, right? The derivative of my integral gets me that integrand, absolutely. So it's just f of x. And guess what? The graph of f is shown, so I can answer all kinds of things about p's behavior, knowing that p prime is the graph that's shown because p prime equals f of x. So let's go ahead and figure out where is p increasing and why. Where is p increasing and why? Go ahead and tell your partner, and then be ready to share with the whole class. All right, so where is the function p increasing, right, and why? Sydney?
-4 to 1. And then 5 to 6.
Raise your hand if you had the same intervals. You had the same intervals? A couple of you, okay. So what would our reason for that be? Right? What would our reason for that be? Courtney? What is positive? Absolutely, because p prime equals f is positive on those intervals. Absolutely, good job. So we always want to make sure that we're using a calculus in our reason. So the calculus would be a derivative, right? One or more of the derivatives. Good. In this case, where does p have a local max and why? Again, I'll ask you to tell your partner, and then be ready to share a reason as well. Calculus justification. Okay, so where does p have a local max? Kobe? So p has a local max, right? P has a local max at x equals 1. Raise your hand if you had that. So at x equals 1? Good. So what would our justification for that be? What would our calculus reason be? Riley?
Well, p prime equals f of x changes from positive to negative.
Absolutely, because p prime equals f switches from positive to negative. Therefore, I know p switches from increasing to decreasing, and that signals the location of a local max. Awesome. Can we find p of 5? Well, I hope so. We're given a function definition for p, defined to be the integral of the area accumulated from lower limit -2 scanning to upper limit x of my integrand function whose graph is shown. So I'll simply start at my lower limit, in this case -2, and I'll scan up until my upper limit 5, accumulating area as I go. So let's go ahead and start that scan. Here I am. And I'm moving from the left, the lower limit to the upper limit, in this case left to right. Great, so I can remember all the stuff from AB. Well, I'll accumulate area such that scanning from left to right, area above the x-axis counts as a positive contribution to the value of the definite integral, and area below counts as a negative contribution. So let's count. 1, 2, 3, 4, 5, right? That's a half times base times height, so that's 5 units minus a half, so I'm back to 4 units, and now I'm going to 5. So now I'm back to 0, so I'm at -1. I'm at -1. Raise your hand if you already had -1. -1? Good job, you guys. What questions do you have about interpreting our function as an area accumulator? So when we have our function, right, defined by an integral expression, when its lower limit is constant and upper limit is a variable, we can interpret that as an area accumulator function and use our relationship with the fundamental theorem of calculus antiderivative part to answer all kinds of questions. All right, now let's switch gears for a minute, and we're gonna develop the average value of a function. So I want you to recall the mean value theorem for derivatives. If g is continuous on the interval a to b, which we just had last unit, and differentiable on the open interval in between a and b, then there exists an x equals c such that algebraically and then graphically. What I want you to do is go ahead and write down the algebraic conclusion while I draw the graphical conclusion. So you guys go ahead and write down the algebraic conclusion. Oh, that's so heavy. All right, so what do you have for the symbolic, the algebraic conclusion of the mean value theorem? What would that look like with F's and A's? Nope, with G's. What would that look like with G's and A's and B's? G's Louise. So what's that look like? Tyler?
G of B minus G of A over B minus A equals G prime of C.
Awesome, thank you, Tyler. So I've drawn my red tangent line, the instantaneous rate of change of G at a particular place, in red to match the symbolic representation. G prime of C is the instantaneous rate of change in my green function G. Then this slope of the secant line is blue, right? That's our blue slope of the secant line is given by G of B minus G of A all over B minus A. Awesome. So we've got our graphical representation, and then we have our algebraic representation. Great. So today we're going to go ahead and now move this towards the mean value theorem for integrals, okay? And we're going to make a connection between the two. Actually, you guys are going to make a connection between the two, and that's one of our goals for the class. So last time we calculated the exact area under the function f of x is given by x squared plus 1 on 0 to 4 using the evaluation part of the FTC. Let's do that algebraically, non-calculator right now again, just to warm up. So let's find the exact area on 0 to 4. So we'll find the exact area on 0 to 4 in between the function f and the x-axis using the evaluation part of the fundamental theorem of calculus. Well, I know that exact area is represented by a definite integral. The integral from 0 to 4 of x squared plus 1 with respect to x. And to evaluate that, I can simply find an antiderivative function for my integrand. The antiderivative for x squared plus 1 would be given by x cubed over 3 plus x, evaluated from 0 to 4. We'll go all the way through my my antiderivative function with my upper limit. So that would be 4 cubed over 3 plus 4 minus, and we'll go all the way through with my lower limit. 0 cubed over 3 plus 0 is 0. And I'm getting 64 thirds plus 4, and 4 is 12 thirds. So I'm getting 76 thirds non-copper. Raise your hand if you got that. You guys get 76 thirds? That's good news because that's what I remember from last class. 76 thirds. What does this represent graphically? So what's the 76 thirds represent graphically? Riley?
The area under the curve.
Yeah, absolutely. So this is the area in between the x-axis and x squared plus 1 in between the x values 0 to 4 exactly. Okay, that's the exact area. Thank you. All right, so that's for you. Now consider a single rectangle drawn on 0 to 4 that has this same area. What would its perfect height be? I'm hearing those perfect height parts, right? Right? And that's ringing some bells. Some of them nice, some of them not so nice. So let's go ahead and this year I'm confident, this year, boy, that we're going to make the connection. So we want to draw a rectangle, right, that has that same area, that 76 thirds is its area, right? We want to draw that rectangle on the same interval 0 to 4, and I want to figure out what its perfect height would be. Can we do that? I think we have enough tools. So let's go ahead and go on 0 to 4. 1, 2, 3, 4. And how tall would it have to be? Well, I know that in general, the area of a rectangle is base times height. And in my picture, the width of this rectangle is 0 to 4, so isn't the width 4? Yes? And isn't the area of that rectangle we want to be the same as the exact area underneath the curve, which we just found was what?
76 thirds.
So if the exact area A is 76 thirds and the width of my rectangle is 4 units, can I figure out its height?
Yes.
Yes, I can, baby. I'm going to go ahead and divide by 4, right? I'm going to divide by 4, and I'll get 15 plus 4 is 19. What are you guys getting?
19 thirds.
19 thirds? So we're getting h equals 19 thirds. Okay. So now let's go ahead and figure out where 19 thirds is, because I want to figure out this perfect height. And I want to draw my rectangle, carefully sketched on the given graph. We'll label its height and width. Okay, so here we go. So 19 thirds is 3 goes into 19 6 times with 1/3, so 6 1/3. Let's do it. So 6 1/3 would be 1, 2, 3, 4, 5, 6 1/3. Yes. This is a job for math tool. Blue, pink. Let's do pink. And I want to do 6 1/3 is going to be right there. Exactly. And right here. And right here. And right here. All right. So what's the width? What's the width of my rectangle, Riley? 4. And what's the height of my rectangle, Tyler?
19
Yeah. All right. So the height of my rectangle is 19 thirds. The width of my rectangle is 4. And the area is, well, it should be 4 times 19 thirds. 4 times 19 is 40, 36, 76 thirds. Okay. So big what, right? What's the big deal here? Well, an average value of the function, right? An average value of a function would be if I could sum up, right, all of those function values over the course of the length of my interval, right, and divide by the number of those function values. Well, there's an infinite number of function values, but the good news is that calculus and limits allows me to work with infinite quantities or infinitely small quantities through limits. And so the average value y of a function is given by the definite integral of that function, right, who I'm trying to find its average value of, over the course of the interval, and then divided by the length of the interval. This is going to connect exactly to the picture that we just drew if we have our width being my b minus a was 4 units, right? And what was the integral from a to b of f of x dx? Well, we evaluated that, and what did we get? 76 thirds, right? And so what would we get for the average value here? Well, we had that average value all along, right? That y average value was the, what about my rectangle? That was my perfect height, right? And so my average value is the perfect height. Marissa, good feelings, not bad. So my perfect height is simply the average value of a function on the interval. Now we could go on to answer more things like where on the interval, at what x value is this attained, and so on and so forth. But visually, I want you guys to see this. And so our mean value theorem for integrals is directly connected. It says that if f is continuous on a to b, then at some point x equals c on my interval a to b, the function, right, the function equals that average value. So someplace my function f attains that average value y average from the last slide. Again, the average value is given by the definite integral of my function on the interval a to b divided by the length of that interval. That's pretty sweet. Awesome. So that's printable for you. Let's go ahead and do it then. Let's find the average value of f on a given interval. In this case, let's use the function f of x given by the square root of 1 minus x. Can I find the average value? Well, certainly. In general, my average value, call it y-av. Your book calls it av f for average value of my function f. I'll call it y-average to be consistent with ab in the Forster text. So my y-average is given by 1 over the length of my subinterval, interval, times the integral from a to b of f of x with respect to x. So I can find that now by doing 1 over b minus a times the integral from 1 to 5 of square root of x minus 1 with respect to x. And I have all the pieces. I know how to evaluate that 1/4. I know how to evaluate a definite integral non-calculator and algebraically. I'll simply find an antiderivative function for my integrand function. This looks like power rule. So long as I have the derivative of the base, in fact I do, it's 1, right? I can add 1 to the exponent and divide by the new exponent. Interpreting that square root as a quantity to the 1/2 power, I'll add 1 to the exponent and get 3/2 divided by the new exponent is the same as times by 2/3. So I'm getting 2/3 quantity x minus 1 to the 3/2 evaluated from 1 to 5. Is that what you guys are getting?
Yes.
Let's do it. Sydney, I told you I was feeling non-calc. Bam! Look at us go. So can I take the 2/3 out too? You guys are going to get upset if I take that out right now or leave it in? Don't take it out or take it out. Let's take it out so we don't trip on it. That is just a multiplier, right? And now let's evaluate through. So I'm going to do 5 minus 1 is 4 to the 3/2 minus 1 minus 1 is 0 to the 3/2. I'll go gadget arm, and I'm getting 2 over 4 is 1 over 2, 1/6, and I'm evaluating 4 to the 3/2 can be done exactly and algebraically by purposely applying the denominator of my rational exponent as an nth root first, so it's the square root of 4, 2, and then raising it to my numerator exponent is 3, so I'm just getting 8. So 4 to 3 halves is 8. So I get 8/6, which reduces nicely to 4/3. So sweet. What does this have to do with the mean value theorem for integrals? If anything. What does this have to do with the mean value theorem for integrals? Well, can we put the pieces together? Can we draw the corresponding rectangle on 1 to 5 with the height equal to the average value of f on the interval? What's the area of that rectangle? And write an integral statement with f that represents this area. So let's do it. We just figured out that the average value is 4/3. Well, the average value is the, Marissa, the perfect height of my function, or I'm sorry, of my rectangle, that when multiplied by the width of my interval gives me the exact area underneath the curve. And there's my connection with the mean value theorem for integrals. So let's do it. Ready? 4/3 is going to be what? Right about 1 1/3 is right here. Orient. All right, let's do it. So, but I'm going from 1 to 4.
Wait, 1
to 5. Give me the money. I don't.
Oh.
1 to 5. 1, 2, 3, 4, 5. Yes?
Yes.
Ah! Yes? If I had a shovel, right? If I had my calculus shovel, and I lopped off this top part where my curve was above my rectangle, right? And gathered that and smushed it, scrunched it on down into this place where the curve was beneath my rectangle, it would fill it up exactly, and I would be left with the exact area of the rectangle. What's that? It's the 4/3 times
5.
16/3. What's the exact area underneath the blue function on 1 to 5? 1, 2,
Say it
3.
again.
What's the exact area underneath the blue graph on the interval 1 to 5?
16/3.
16/3. Write an integral statement with f of x that represents this area. Can we do that?
Yeah, let's
What would it be? Kobe?
Integral from 1 to 5.
Absolutely. So my integral statement, these are equivalent. The area of the green rectangle is equal to the red shaded area. It's the exact area. Awesome. Okay, so how are the mean value theorem of derivatives for derivatives? Come on, Tiger. How are the mean value theorem for derivatives and the mean value theorem for integrals related? Well, let's go ahead and get those on our little chart here. So I'm trying to make a chart and I wasn't sure how it was going to fit on your note sheet. So we want the symbolic representation. We already did that to warm up. The graphical, we already did that. Now we want to go ahead and connect it with integrals, right? The mean value theorem for integrals and its graphical representation. And then you guys are going to, right, see the connection there. So for derivatives, we already used g, didn't we? So we could say that g prime of c is equal to g of b minus g of a all over b minus a. Graphically, I'm going for it. No, I'm going for it. Can't stop me down. Graphically, we want our slope of the secant line
That just got me.
to be the same as the slope of the tangent line. How are we doing with the derivative?
Terrific.
Okay. Can we make a connection now between the mean value theorem for derivatives and integrals? Well, what's our mean value theorem for integrals, right? It says that if I've got a continuous function f on my interval, then there's got to be some place, x equals c, where the value of the function is equal to the average value, right? The average value of the function. What's the average value of the function? I'm going to write with s just right really quickly because that's what we have, and then we're going to make our connection. So I'm going to go ahead and write the function takes on the average value, which is given by 1 over b minus a, right? 1 over b minus a times the definite integral from a to b of f of x with respect to x. Okay.
Bless you.
Graphically, bless you. Graphically, what does that look like? Well, for us, I have if I could make drawings. Clearly I can't, but if I could make drawings, pretty drawings, then the exact area underneath that blue function, right? The exact area underneath that blue function in red, dotted in specs, would be equal to the area of the green, right? The area of the green graph. So where's my connection there? The red dots are the exact area underneath the curve. Yes? So the red dots are the exact area underneath the curve. The b minus a is the width of my rectangle, right? So then what's the height of my rectangle? F of c, this y average is my height of the rectangle, all right? So I'm dying to get over there, right? What am I missing here? Yes?
Big F of B minus big F of A over B minus A.
Would be right here?
Yeah.
Yeah. Yes! This big F, right? This big F of B minus big F of A would be what? G, right? This right here, so long as the derivative of G is F. And so this part right here could be my G of B minus G of A. So there we go. We've got all the pieces. And so here is my thing, which means that the G prime of C is what? Because now these are equivalent. The right hand sides are equivalent. So what's G prime of C? It's F of C. It is my average value, right? It is my average value of F, and F is the derivative of G prime. And so watch it. Watch it. No, now watch it like that. Okay, so here we go, right? We have come full circle. So if F is integrable on A to B, its average value is given by blank. If F is continuous on A to B, then at some point x equals C on A to B, then there's my mean value theorem for integrals. And then one practice. Let's go ahead and find y average given a function on an interval. I'll pause the recording while you have this, and then I'm going to resume it so you can share your responses with the whole class. Go ahead and share our average value formula then. If f is integrable on A to B, its average value is given by what? How could we write that? Vivian?
1
Raise your hand if you had the same as Vivian for number 1. There's our y average. Good. If f's continuous on a to b, then at some point, right, on my interval a to b, at x at c, my function must attain that value. So how can I write that? Right? What would that look like, Riley?
F of c equals f of b minus f of a over b minus a.
Big F. Yes.
Big F. B.
Because it would be the integral of.
Okay, yeah. Big F of b. Big F
Awesome. I'm going to write it like this because, no, Riley's right. Isn't the integral from a to b of f of x with respect to x big F of b minus big F of a, right? So that's absolutely right. I'm going to write it like this just because that's how you see a mean value theorem for integrals. But that was our connection that we made. That was the point. This is, right? This is big F of b minus big F of a, or in our notation, g, right? That was g of b minus g of a. Awesome. And let's go ahead and find then the y average given a function on the interval. So we know our y average is in green, the Vivian provided us with. So we can go ahead and calculate that y average simply by taking 1 over 1 minus 0 times the integral from 0 to 1 of f of x with respect to x. I know an antiderivative for 1 over x squared, right? Is this a power rule problem?
No.
No, what is it, Sydney?
It's an inverse tangent problem.
Good, and so this is inverse tangent of x, which differentiates to 1 over 1 plus x squared, evaluated from 0 to 1. And so what does that happen? Well, inverse tangent of 1, right? The inverse tangent of 1 asks me what angle has a value of tangent that is 1, minus the inverse tangent of 0 asks me what angle has a value of tangent that is 0. And thankfully we know each of these, right? Where is the value of tangent equal to 1? The sine and cosine are both square root of 2 at this angle. What's the angle measure though? Absolutely. So pi over 4 minus, and the inverse tangent of 0 is 0. So I get pi over 4. Raise your hand if you already have it. Do you have pi over 4? Woohoo! No?
No.
So
I ended there.
unit circle fresh, right? Unit circle fresh. Stay fresh with the unit circles. And we've got that. Now, did you get this printable? I tried to redo it, so yeah, I use all kinds of paper. Great work, you guys. There are some tricky ones on the OTL, and I want to structure in time that so you talk together. If you'd like to move your seats so that you may work together, you may. If you want to stay in the same place, you may. If you want to work alone, you may. So I'm going to go ahead and save the recording and post it to our Moodle site.